There's RR, which is basically a reverse debugger.
It helps you put bugs into your program? What's a reverse debugger?
Sounds like fuzzing.
A debugger that goes forward, you basically say step and it goes forward one instruction, right?
Oh, right. Yeah.
Well, a reverse debugger allows you to say step back and go back in time to what happened before.
Oh, time-traveling debugger.
Exactly.
That sounds amazing.
It is. It's incredible. It's like a fantastic bit of engineering.
This episode is brought to you by our friends at SourceGraph. They recently launched a new feature called Code Insights. Now you can track what really matters to you and your team in your code base, transform your code into a queryable database to create customizable visual dashboards in seconds. Here's how engineering teams are using Code Insights. They can track migrations, adoption, and deprecation across the code base. They can detect and track versions of languages or packages. They can ensure the removal of security vulnerabilities like Log4j. They can understand code by team, track code smells and health, and visualize configurations and services. Here's what the engineering manager at Prezi has to say about this new feature. Quote, as we've grown, so has a need to better track and communicate our progress and our goals across the engineering team and the broader company. With Code Insights, our data and migration tracking is accurate across our entire code base, and our engineers and our managers can shift out of manual spreadsheets and spend more time working on code, end quote. The next step is to see how other teams are using this awesome feature. Head to about.sourcegraph.com/code-insights. This link will be in the show notes. Again, about.sourcegraph.com/code-insights.
Let's do it. It's go time.
Welcome to Go Time, your source for diverse discussions from around the Go community. We record live on Tuesdays at 3 p.m. U.S. Eastern Time. Subscribe at youtube.com/changelog so you don't miss it. And don't forget to follow the show on Twitter at GoTimeFM. Special thanks to our partners at Fastly for shipping our shows super fast to wherever you listen. Check them out at fastly.com. Okay, here we go.
Good evening, morning, and afternoon, everyone, and welcome to the episode about static checkers. Hello to Matt, my co-host for this episode. How are you doing?
Hello to you, Natalie, also. I'm good, thanks. How are you?
Great. I enjoy all the plants we have in the background. Hello, Matan, our guest for today. Welcome.
Hello, and thank you.
How are you doing?
I'm doing pretty well. It's kind of late, but yeah, it's been a long day. But I'm doing good.
And you are joining us from?
I'm joining you from Haifa, from Bat Galim. You can see the sea from that window over there if it wasn't so dark outside.
Oh, wow.
So all the way from Israel. And I see you don't have plants in the background. Instead, you have ducks, which you probably use for duck debugging, as one does. And you have two, kind of one is white and one is red, for everybody who's listening but not watching. So this is the one who says, just force push the commits. And the white one is like, no, run one more test.
There are three of them. One of them is a panda duck.
Ah.
Oh, yeah. Panda duck. Oh, yeah. It does look a bit like a devil.
And the blue one is just in case you're in the blue team, which is kind of decent code, not too tested, but not force push. Sounding
yeah,
good.
It seemed to balance out the red one.
We had an offsite recently at where I work, and it was in Amsterdam. And the souvenir that we got everyone was a little rubber duck, each kind of tailored to each person. So,
wow.
Yeah, it's a very nice gift, but it's very useful for rubber ducking, like you mentioned, Natalie.
It sounds very thoughtful.
Yeah, it is. Well, it makes them better programmers, really. I don't know why. Do they teach that at university? Do they teach rubber ducking?
I teach it when I TA students, and sometimes I have to help them with their homework. Then basically I have them, just explain the problem to me, and through the process of them explaining it, they understand what the problem is. And then I tell them, well, next time you should try that with a rubber duck.
Just leave it there. Don't elaborate.
Just in your reception hours. Here's a rubber duck. Speak to it.
Good idea. You could just have that in your office.
A weird thing I learned about rubber ducks is that if you actually put them in a place with water like a bath, you want them not to have the hole that allows them to squeak, because this is how they get moldy.
Oh, really? Why? Because water goes in.
Yeah, and it's not very well ventilated. So if you do plan to bring it into a wet room, then make sure that it does not squeak.
So if you're a programmer and things aren't going well and you're trying to rub a duck and you're crying a lot, keep the tears away from the duck because it could go moldy.
This would be step 10.
Yeah.
I can think of a few other things you should do before that, but it can be on the extended list of things you might want to do.
Yeah, good point. Tissues, hairdryer, loads of ways to.
Taking a walk.
Oh, yeah. That is a good hack, actually. If you're stuck on something, go for a walk or think about something else. How many times do you hear people say, just in the shower or even like asleep, like sometimes I was able to solve these problems? It's taking a break is important. And that's really counterintuitive because you feel like you have to work on it to solve it, don't you?
Yeah. But you feel pressured somehow usually. And that pressure prevents you from thinking clearly. And taking a walk is usually a bit hard because you need to force yourself to stop thinking of it and focus on meditation or walking or nature. But then your mind has a chance to process whatever it is you were doing and maybe come up with new ideas.
Trying to see what's a good way of tying that to the subject today, but I have yet to find a good one. So in a less smooth transition, no jokes. Matan, you are a PhD candidate at the Technion in Israel, and you're researching metaprogramming and static analysis. You have worked in all sorts of interesting companies, and now you're back in the academy. So tell us a little bit, what did you study? What did you do afterwards? Why going back to studying after being in the industry?
So for my bachelor's degree, I did computer engineering because I had this, let's call it romantic idea that I should understand how a computer works from, physics to software.
Wow.
And it was very cool and I learned a lot and I liked my degree a lot, but it made it tougher than it might otherwise would have been because I'm a programmer. I did software engineering before I started studying, so I was already good at that, and adding something that was completely new and different like electrical engineering and all the circuit and physics and that stuff, it made it significantly harder. But I still liked it a lot and I think that I learned a lot. And after my degree, I worked in like a startup that my friends did at the time. And then I decided that I needed to experience life at a big corporate. So I went to Google and I spent some time making search features. But eventually I decided that being a code monkey is fun and I like that. But I also want to experience research and see what like life at an academy is like and what they're doing in like graduate degrees. So I went back and for my master's and finished that. And now I'm in my PhD and I like it. I don't know if I'm going to do this forever, but for now this is fun. And I get to, play in my sandbox and make sandcastles and toy around with my own like toy ideas, which is what I like about academics.
You mentioned Code Monkey, and I have to make the joke now because I still feel overdue from the less than smooth transition from before. Have you tried being Code Gopher?
Stackadish.
Fun. So what was your master's research topic?
So my master's research was making a programming language. It was in programming language design. What my programming language did was it took, like slideshows and I wanted to add animation and I wanted to basically make a language that describes what the animation is, what the motion on the screen is. I liked it. It was fun working on it, but let's just say that its main purpose was to get me a master's degree and that it didn't turn out to be especially usable. It had a couple of really cool ideas. For example, the idea was that I could build a big animation from basic parts and that if I wanted to make a change in the animation, as anyone who ever used PowerPoint and put animations using the animation pane knows, making it is fine. You can add the animations, but if you want to make a change like in the middle, if you want to push something in the middle there, then basically you have to start over and sync it all up to what you were doing before. And I wanted it to be able to tell it, add this thing in the middle and calculate everything according to this change. So I had like a few cute ideas in there of like making it like a physical system of springs where you can add a spring and everything basically reacts based on the change you've made. And it worked and it was nice, but it was not it was not a production system, let's put it that way.
Because it had no tests.
I actually did have tests. It's just that basically you had to think like me in order to use it and think like me at that very specific time of me writing it.
So how important is that to you then? Because you talk about like you like being in the sandbox, building sandcastles. How much of that is anchored back to something that could be practical or useful?
Well, that's a good question. So my thinking is that I wanted to be anchored back to something that is practical and useful, right? But I'm okay if it's not. I'm okay going off into the wilderness and exploring and finding out things. And if it turns out that they're not impactful and like they don't make money, then that's okay too. Ideally, in my dreams, then I want to go out and make something that everybody would know and use and like be important and useful and stuff. But I'm okay with it not being. And it's basically taking a chance and not knowing how it's going to turn out.
Kind of like startup attitude, really, that has that. And being able to fail and having that freedom to fail is quite important. Gives you that extra permission almost to do things that otherwise people might not have a chance to do. Yeah.
So like in one sense, I think startup culture is about being small and agile and being able to push yourself into a niche that a bigger company just wouldn't fit into because they can't be flexible enough to think about it that way, to allocate resource for that thing. But on the other hand, like I think that startups always think in terms of MVPs and like making usable things and making products, where in academics, what you want to do is always write a paper. You want to have like an experiment, results, data that you can tell other academics about. And usually in order to tell other people about what you're doing, you don't need to build the full product. You don't need to have users. You don't need to do any of that. You just need to make your specific experiment and write it up well enough so that other people find it clear and interesting. And that's it.
That sounds a lot like blogging about fun projects that you have.
It's blogging on steroids. It's blogging with a lot of formality added. And that's why, science communication where scientists blog, that's a thing that's happening. So, like academics usually love to write. Like that's what they do in their day-to-day. They're usually good at it and they make blogs. And academic Twitter, for example, is a thing.
Oh, I bet that's amazing. Is it good?
Yeah, if you're interested in that sort of thing.
Have you been tweeting about static analysis tools? Or static analysis in general? Or wait, maybe we can start with saying what is a static analysis?
So static analysis is basically what we want to do is figure out certain properties about code. And a property can be like, at its most basic thing, does this program have a bug? Or like, does this program succeed? And we want to do all that statically, then that means without actually running the program, because running the program might have side effects. It might do something that we don't want to do right now. It might take a long time. We just don't want to run it yet. The program might not be even finished. We can't run it, and we still want to know things about it. So static analysis can be anything from where this function is called to like, is this program written the correct style, which is something that's not that big of a problem with Go because we have like Go format, which is supposedly also like a static analysis tool. But other languages have things like linters, which tell you that, well, your indentation is incorrect here. And that's also a thing that happens. But static analysis can also be a part of refactoring, where you want to rename a method and you want the IDE to find out where all the calls to this method are and use static analysis to find that.
Yeah, right-click refactor.
Exactly.
episode is brought to you by our friends at Square. Millions of Square sellers use the Square App Marketplace to discover and install apps they rely on daily to run their businesses. And the way you get your app there is by becoming a Square App partner. Let me tell you how this works. As a Square App partner, you can offer and monetize your apps directly to Square sellers in the app marketplace to millions of sellers. You can leverage the Square platform to build robust e-commerce websites, smart payment integrations, and custom solutions for millions of businesses. And here's the best part. You get to keep 100% of revenue while you grow. Square collects a 0% cut from your sales for the first year or your first 100 Square referred sellers. That way you can focus on building and growing your Square customer base, and you get to set your own pricing models. You also get a ton of support from Square. You get access to Square's technical team using Slack. You get insights into the performance of your app on the app marketplace. And of course, you get direct access to new product launches. And all this begins at changelog.com/square. Again, changelog.com/square.
Static analysis must be easier on typed languages then, that are strictly typed, versus languages that are dynamic, that have a heavy runtime element. Is that true?
Oh, yes, definitely, because type checking is also a type of static analysis. So basically, by having types, you're giving the tool a lot more information that it can use. And if it has more information, then it can do more stuff. So like one of the basic truth of computer science is that static analysis is impossible. You have the halting problem, which Alan Turing proved way back when, which says that basically you can't make a program that says if another program will halt.
Mm-hmm.
And the proof of that is very cool because basically he said that, well, if I had a program that could do that, then I could put itself into it and that will lead to a logical contradiction, so we can't have that. And a corollary to that is the Rice theorem, which says that you can't prove any interesting property, like any interesting as a non-trivial property about a program. So you have this strong theoretical basis that says you can't do that, and yet you have this rich scientific field where like we do that every day. It's not a problem. It turns out that the interesting programs, like the ones that real software engineers write, they're simple enough that we can analyze them. But what that theorem means is that we can't be 100% sure. We have to like make some sort of concession. We have to have some program where this won't work within our limitations. So for every language, if you do crazy enough thing with what's it called when you reference the method by its name instead of like calling it
reflection.
Yeah, if you have enough reflection, if you do enough pointer tricks in C, you can always confuse it enough that it doesn't work. But that's fine because for like 90% of the programs it does work, and that's usually good enough. We're talking about static analysis, not verification.
And how does this field tie to your research? Or what is your research about?
So what I want to do in my PhD is metaprogramming using static analysis. And when I say metaprogramming, what I mean is code that write code or code that changes code. So basically refactoring, and also refactoring usually means that you change the code and then you work on that change version, but you can also like have a compilation step that changes the code and you never work on that changed version, right? So that's what I mean by metaprogramming, all those things that make code, change code, templates, maybe even generics, things like that. And what I think is that basically making them aware, having them use static analysis information can make them more powerful, more efficient. So I can, for example, say, one of my initial examples was making reactive programming. So let's say I have this class, and in this class there's a field, and it has a getter. And what I wanted to do is I wanted to send me an event somehow every time the field changes. But the class is not written that way. Like whoever wrote it just wrote a getter and you have to poll it. And what I want to do is I want to find out every way that this field can change in the program. And every time that it changes, I wanted to send the event so I can know when that happens, that it becomes reactive. So if you can do static analysis and modify the program based on that, then you can easily do that. And that's basically my goal. I want to enable things like that, and I want to make it in, let's call it a declarative way that I can build using basic building blocks, more complex behavior.
It sounds really interesting. One example of static analysis I've seen, because you mentioned quite a few, and I actually hadn't considered even like formatting as one of those, but of course it makes sense. One of the downsides to the GoFumt tool is if the program is incorrect, it doesn't work. The program has to be
well-formed.
Yes, thank you. It has to be well-formed. So any kind of static analysis that can happen without that being the case, I find that to be quite amazing, because often it relies on the same kind of packages that analyze the program for compilation to do static analysis. Is that right?
Definitely. So like handling things that are partly correct or like are partly complete, even like they're not incorrect, they're just missing a bit, and you want to take just the parts that are there that are good, is hard. One of the other projects that I'm currently working on it has to do with pseudocode. So what we want to do is to compare pseudocode to actual code and see if they match. So that's kind of a similar idea, because pseudocode obviously is not, doesn't have perfect syntax. Or
I use occasionally GitHub Copilot, and that actually does quite an interesting job of like the code can be wrong. In fact, you can give it context just by writing comments or just by the names of the functions that you use and the variable names and things. So that definitely feels magic. I guess that's different because I suppose that's the ML doing that work, right?
Yeah. So ML for PL, or however you want to call applying machine learning to code, it's interesting because on the one hand, like code, so a lot of the techniques that are used there come from NLP, from natural language processing, which obviously makes sense because, this is text and this is text, and like you won't use techniques that come from image processing. That has nothing to do with it.
Right.
But on the other hand, code is very structured. It's very hierarchical. It has properties. In order to compile, it has to be very strict in various ways. So giving up all that information, all that context is silly. So you do want to use it in their, let's call it non-machine learning approach to static analysis, to dealing with code, is called formal methods, which is basically taking ideas from logic and those sort of areas of math and applying them to code. And that's where all the things like type checking and that come from, and like all the theory behind it. I don't understand 100% how Copilot works. I read their white paper. It's very interesting. I don't think that they, like, on the one hand, one of the points of machine learning is that they don't do anything specific. They don't say, oh, look, there's a type. They want the machine learning to somehow learn that themselves.
Yeah.
But on the other hand, I think that they do try very hard to make sure that the algorithm has access to like type information and things like that.
Yeah, it's funny because it gets things right that are really surprising, and it makes mistakes that a simple static analysis tool wouldn't make. It still does make those mistakes, and I'm sure they'll keep working on that. It's almost like there'll be an extra check after to see whether this even is valid code. It does get frustrating sometimes because it'll kind of guess arguments to a method that are wrong. They look like it's the thing it's seen before, but they aren't the method. They aren't the arguments for that particular method. So just a quick check would have found out that wasn't going to work. And I suppose that's what they'll do. But that is interesting. You do see clues, really, of what it's doing with some of the mistakes it makes. But I mean, it is amazing, I have to say.
Yeah, and the code that it came from, what it is that it learned that would make it answer in this way, right?
Yeah.
Yeah, it's actually exactly the point that I wanted to bring up, like all this AI creating code, right? So Copilot is based on Codex. This is the engine that is running behind it. and a little bit from under the hood of how things are going on there. The plugin for Copilot is collecting some context, which is not known. This is kind of the secret sauce. And it's being sent with some extra instructions, which are also not known, to that engine, to Codex, which is probably the article that you read, Matan. And sometimes you can see, because it collects the wrong context, it provides something that it saw in the past but is not relevant for your code, like what you said, Matt, about the signature of a function that could have been easily caught. And it actually makes a lot of sense that the next good step of this, such a development of such a tool, and Copilot is one of the tools that rely on Codex. There are other tools out there that use that, would be exactly creating static and maybe in the future even dynamic checkers. But definitely the ability of not needing a full working program in order to run such a test is a huge deal for that next step. So this is super, super interesting.
Yeah, by the way, when I first learned about Copilot, for some reason I read it as copy lot, like it copies a lot. I thought it was like Camelot. So I completely misunderstood that it said Copilot. I was using it for ages as in the preview and thought it was called Copilot. It's quite nice.
So one of the companies that I worked at during my master's, like I interned there one summer, they used to be Codota. Now they merged with / bought out / became Tab9, and they're making like a very similar to Copilot tool. And they have the same ideas, only I think that what they do, knowing behind the scenes, is like their algorithm is a bit less blind than Copilot. So you can't have it do things like, the advertisements for Copilot where you write the documentation for some function and it just completes the function for you. But you can make it do things like, you start a database connection and it completes all the boilerplate for you and things like that, based on other examples that it has seen. And it does use more type information and names and things like that.
Oh, it's so clever. One example I've seen of static analysis that surprised me and actually got me quite excited about it was an example case where if a variable at any point in the program is called password, and then at some other point in the program it's logged out somewhere, that would be then a warning that it would say, oh, look, this variable, whether it's called now, this is being printed. At one point somewhere by just sort of analyzing the code, this was a password. And so is this really what you want to do? And I found that to be actually really quite interesting, like that, because that is very useful.
Yes. So Perl, if you remember, or if you ever used it, has like this whole idea where you need to sanitize your input and bless them and things like that. Because they had this idea that if you take input and you don't use it carefully, then it could affect the program in ways, SQL injections and all the sort of thing. And yeah, that sort of static analysis is called taint analysis. And I think that, in recent years, even like that sort of thing has become important, where, you can leak out the password and also just develop like a related but not the same idea, that developers just putting secrets into their GitHub repositories. And that's also something that, just a few, a search might find that, yeah, maybe you shouldn't put it. There are specific places in the environment that you're supposed to put in your secret keys and whatever.
Yeah. And I tell you what, having that early, so we talked about the program doesn't have to be finished for this to work. Having that insight as you're working, that's really when you need it, because that's the point at which maybe you're making design decisions that you'll then have to live with. So yeah, I think that's very exciting. What are some other cool use cases or cool little things like that you can do with this?
Basically, so you can find bugs early. Other programming languages, Rust, if you read about it, like put this whole idea of being very strict with the checking and the static analysis inside the language itself. And you can basically make sure that pointers don't go out of scope and be used, because the language itself is specified to keep track of that. Other things you can do with that is, if you're doing multi-threading and you have mutexes and other locks, you can use a static analysis to make sure that after every lock is both locked and then unlocked, and you don't unlock something before you locked it and things like that. Every allocation is freed if you're using something like C or C++ and you're allocating memory manually. Every file that you open that needs to be closed, then you can check that. Some of those things, like in some languages, you have to check, so it makes sense to have static analysis for it. But in other languages, it's not even a problem because the language itself takes care of freeing resources. But in those languages that do use manual resource allocation, then that makes a whole lot of sense. And of course, memory and files aren't the only resource you have. You also, if you talk to a server by some protocol, then you can have static analysis and make sure that you complete the protocol in the correct way.
What are your thoughts about the static checkers in Go specifically?
So I don't know a lot about Go. I'm technically like a professional Go developer in the sense that someone once paid me money to write some Go.
Oh.
That is the definition.
Yeah, you're one of us.
But I'm not very good at it. So the one static checker that I found for Go is called static check. And it seems to be quite thorough. And it has like a lot of linting options and things that it can tell you that might be wrong about your Go program. So we've talked about all kinds of static checking, and we can talk about levels, but a lot of what static check mostly does is linting. So it looks for certain patterns of things that are dangerous or might be incorrect or probably not what you meant to do. And then it warns about them, which is a very useful thing to do. And it seems that it also has some deeper static analysis because it can, track context of various errors and figures things like that. So it looks like a great tool.
Yeah, there's actually quite a range of them, and some of them are general purpose. Others are very specific, like there's a tool called Error Check that checks to make sure you don't ignore any errors, for example, which is something that, is quite important. And then there's the meta-linter, Go meta-linter, which essentially runs all of the linters and does the static checks. Like you say, it's really linting a lot of it. So we'll put some links to these in the show notes for people interested. But they're integrated nicely into IDEs already, so you probably already have them. Yeah.
So the thing that I find interesting about, I want to do, as a static analysis researcher, is make my own, basically. The linters are great. Everybody should probably use them. Everybody probably does use them because, as you say, they're already integrated into the IDE. But every project has its own thing that it's doing, and it's using a library in some way. It's using an API. And what I want everyone to be able to do is be able to define their own rule set or be able to use a language to define their own static analysis that will warn them of things that might go wrong when they're making code. And for small projects, for scripts, you probably don't need that. But if you need to collaborate between multiple people that might do the thing, if you're a company or you're an open source project, then those things start to make a lot of sense.
This episode is brought to you by Chronosphere. When it comes to observability, teams need a reliable, scalable, and efficient solution so they can know about issues well before their customers do. They need a solution that helps them move faster than the competition. And companies born in the cloud-native era often start with Prometheus for monitoring, which is obviously an amazing piece of software, but they quickly push it to its limits and often outgrow it. They run into issues with siloed data, missing long-term storage, and wasted engineering time firefighting the monitoring system versus delivering their application with confidence. They describe the system as a house of cards, where a single developer's seemingly benign change can overload the whole monitoring system, or they say they're flying blind because they pride themselves on making data-driven decisions, but losing visibility means they lose this competitive edge. Ryan Sokol, VP of Engineering at DoorDash, has this to say about Chronosphere. Quote, the visibility and control that Chronosphere's platform gives us to manage our observability data and costs are a game changer, especially with our unprecedented growth. End quote. Chronosphere is the observability platform for cloud native teams operating at scale. Learn more and get a demo at chronosphere.io. Again, chronosphere.io. And by our friends at Flatfile, the leading data onboarding platform for teams who don't want to build yet another CSV uploader. Flatfile's powerful out-of-the-box solution takes the import burden off of your shoulders, freeing you to solve bigger business problems and build products that people love. Get to usable data faster so you can focus on what matters most to you and your business. It is incredibly fast to set up, just write a few lines of code and get up and running in hours, not days or weeks. It is framework agnostic. Use the SDK to integrate Flatfile into any JavaScript application with support for all major frameworks. Learn more and get started at flatfile.com. Again, flatfile.com.
What are some static checkers from any language that you saw that you really like what they do?
Oh.
What's a functionality that you really like? The static checker that you will build, what will it have?
So one of the harder things to do with static analysis, and it's not like a tool in of itself, it's a way to get there, but it's called points to analysis, because even in languages that don't have pointers, you usually have references, which means that one thing references another thing, and that thing may change over the course of the program. And keeping track of what aliases a certain object in memory may have, it's hard to do when you're coding the program and trying to keep a mental model of the program in your head. It's hard to do when you're debugging and you need to find out, wait, what does this point to right now? And it's even hard to do when you're trying to do static analysis, and that means that you're not even running the program yet. So if you know what this variable points to right now, where is the thing that was allocated, what it is, what's its dynamic type, what thing it really is, then you can make all other static analysis basically stronger, because now they can know more things. They know that, this is a pointer, I don't know, I now know where it came from. So that's static analysis that I think is really cool. It's really difficult because programmers can do whatever they like and you need to somehow constrain this chaos. But yeah, that's what I want to do well.
Yeah, that feels like a problem that would be much easier solved at runtime.
Definitely. At runtime, you just know what it is, right? You don't have to check it. At runtime, you have other problems. Like, let's say you traced your programmer and now you have this huge file of trace of where everything went, and you still have to sort out that trace, to define the way that it looks. Because usually when you're debugging, what you see is that, okay, so I have this value right here, right? How did it get there? Like, the place where the error happens is not the place where you see the error, where you notice that something went wrong, is not the place where the error happened. What you really want to know is all the path, the operation that happens on this value to get it to this obviously incorrect state. And that's hard. And there's RR, which is basically a reverse debugger.
It helps you put bugs into your program? What's a reverse debugger?
Sounds like fuzzing.
A debugger that goes forward, you basically say step and it goes forward one instruction, right?
Oh, right. Yeah.
Well, a reverse debugger allows you to say step back and go back in time to what happened before.
Oh, time-traveling debugger.
Exactly.
That sounds amazing.
It is. It's incredible. It's like a fantastic bit of engineering.
But does it just keep a snapshot of the state at every point, or is it more intelligent than that? Is it because some operations you lose information, I guess, don't you? How does it go backwards in time? Is it time travel?
Basically, that's what it does, right? It keeps operations at every point, but there's so much, bookkeeping that you have to keep up with in order to do that. Yeah. Because obviously, you can't just after every machine opcode keep state, because that will blow up in basically no time at all. And there are other things that the program does, like output to the screen and write into sockets and things like that. So you have to be very clever with how you keep it. So what it basically does is keep snapshots, but not after every point, only before things that input or output. I mean, it figures that the rest of them, it can just calculate from that.
Gotcha. Yeah, that I think that makes sense.
Yeah.
That does sound really cool. I wonder if we've got that for Go. I've never heard of it for Go, but maybe.
So it might just work with Go because, I don't know, let's check.
Everybody's Googling.
Yeah, I think it might work. I found a debugging a flaky Go test with Mozilla RR.
Yeah, because it works at the assembly level. So it cares about machine opcodes, and like if it compiles into machine opcodes, then it can work with it.
That's great.
And yeah, it's hard to use, and you're stuck with a debugger that looks like GDB, which is not the most user friendly of interfaces. But it does work. It does do the thing that it promises to do, which is very cool.
Well, it's a good opportunity for somebody to build a tool or integrate it into an IDE then, in that case, if it's just got that kind of text interface.
Definitely. I'm sure that JetBrains or whoever are on it.
Other IDEs are available.
That's true.
I have to just say that for legal reasons. Actually, I don't think I do, but I say it. Yeah, I bet they are.
Also, if anyone is looking for an interesting talk title for any upcoming conference, I think this is a topic I definitely never heard of.
Yeah, I would love to hear a talk on all this, actually. If Matan's not going to do it, someone should.
Yeah.
Yeah, so that's dynamic analysis. So let's talk a bit about that. Basically, static analysis helps you before you even run your program, and it can help you find bugs, and it can help you just answer questions about what your program is and how it works, and maybe answer a question about queries, finding things within your program. If you have enough code, then just searching it is a task.
Right.
But dynamic analysis is still a hard task. You basically can use the same information that you would use during compile time, but now you have all the real-time values too. So you can, instead of doing symbolic execution and trying to figure out what the values can be, you can actually know what the values are, but you still have to keep track of them. In some contexts, you just print statements everywhere and you're done. And you can look at what your program did and you're happy and you figure it out. But sometimes print statements aren't enough. If you're doing, what's it called, serverless programming.
Yeah.
With Amazon Lambda, and where you write single function and hook them up, and they don't have anywhere to print, and you don't know when they run, and you don't know how they will run, but maybe you can get a trace if you put them together correctly and put something to log. And then you can use this trace to figure out, so I got this bad value from the database, and then it went through 11 different Lambda functions before it got here, and this is where my error came from. So putting all that together is not at all trivial, and you can basically have to build a tool to do that.
Or listen to the episode from last week where Matt was talking about instrumenting.
Yes.
Yeah. So instrumenting is like dynamic analysis, right? You're looking at what is happening.
Yeah, and that's the kind of thing where, if it's running at scale, of course, that's a different picture to just the code or just the single program itself. But yeah, and so just printing lines out, that is kind of dynamic analysis, I guess.
Well, it is. It's a very primitive form of it, and it's not augmented by tooling, let's say it like that.
Yeah.
And making tools for making our jobs easier is like what we do as programmers, right?
Yeah, absolutely. That is interesting. I mean, there's like structured, we even try and do it with structured logging, where now we are putting structure into the log output so that we can use that more later. Yeah.
Yeah. And then this structured log is almost like a trace, right?
That's definitely an interesting view on that. And also, instead of saying I'm just printing things, you can say now I'm dynamically debugging.
Yeah, I'm doing dynamic analysis.
Mm.
Yeah. But would you say Hello World is a dynamic analysis program? That's all it is, isn't it? That's probably the simplest.
But what information does it give you?
It says hello.
I guess it just prints tell you when you entered the function and when you left the function, and that's a trace, right?
Yeah, that is a little signal, isn't it?
Yeah.
Yeah, that's a good point.
Maybe it can be fun to add a timestamp to those. Then it's like a proper log.
There you go. If you use the log function, if you log print line or something in Go, you get the timestamp for free. You could use Go in your work because one of the nice things about Go is it's an open source language. You have at your disposal available all the packages that the Go toolchain itself uses to understand Go. Go actually now is written in Go. Talk about meta programming. Go, it used to be written in C, now it's written in Go. I can't wait for the initial information to be lost in generations' time, and they just know that Go is written in Go, and no one knows how. I love the idea of that.
They will use RR to go back.
Yeah.
No, wait. Once you said that, I have to tell you about what I think is one of the coolest things ever, and that is a talk called "Reflections on Trusting Trust" by Brian Keringham.
Also available in the show notes.
Ken Thompson, sorry. It's based Ken Thompson. So it's a thing that compilers for languages should be written, or compiler writers like to write them in the language that they are compiling. So this is called a self-hosting language. And it's basically a milestone for a programming language to have a self-hosting compiler, because it means that the language is sophisticated enough to write a compiler for itself. And writing compilers is one of the classic computer science problems of complexity. Let's call it that. And the idea behind Reflections on Trusting Trust is that the C compiler is written in C and it compiled itself. So if you added a backdoor into it, for example, every time that it tries to compile the login program, then it also adds like a little backdoor that accepts a username and password that is known, then that compiler would insert a backdoor into code that is, and the backdoor would not be in the source code of the login program. That's not good enough, because then the source code of the compiler will just show you that it's doing that, right? So we can't have that. So what we could do is add another backdoor into the compiler where it adds a backdoor into itself when it compiled itself. That both adds this backdoor and adds a backdoor for the login program. And then you would have a backdoor that is basically undetectable unless someone is especially fond of reading, assembly language, of compiled assembly language, not even handwritten assembly language with comments, just compiler output. The backdoor would appear nowhere in source code. It will always only be in the binary. And you can't just, recompile the compiler to get rid of it, because it would keep adding it.
Oh, wow. That is awesome. That's really creepy.
It is.
It's like a Black Mirror episode, really, or something like that, isn't it?
Yeah.
There must be some virus, some hacking software that is using this. And it seems to have been around for a while.
Yeah.
Yeah, he wrote that in 1984.
So it's been around so long that there have been anti-reflections of trusting trust ideas, where you basically have to use multiple compilers to get one verified output. And there's a whole slew of ideas that combat this. But if you like these ideas of things that reference themselves and things that
Matt does,
then there's a book called Gödel, Escher, Bach, which I can't recommend enough.
Joining the recommendation for sure.
Yes.
That is a very interesting one.
I love that book. I agree. It's bonkers. It's so good.
If the three of us agree.
Yeah, there you go. This doesn't sound... Go on, Natalie. If all three of us agree.
It does not sound like an unpopular opinion.
I actually think you should probably leave.
You have to agree this one was smooth.
Brilliant. That's the best one yet.
This also is another popular opinion. Okay, Matan. So as a preparation for this episode, we asked you to come up with an unpopular opinion that does not have to be related to Go or programming or anything like that. So we're ready to hear. What is your unpopular opinion?
So my unpopular opinion is that after going through all that, hyping up static analysis and all the things that it can do, my unpopular opinion that it actually doesn't work. Like it works up to a point. Like it does all the cute things, it does the simple things, but you can only make it so complicated before it all breaks down and you get to keep the pieces. And that's true for if you try to do it using formal methods and if you try to do it using machine learning. No matter what you do, you're still stuck thinking very hard and trying to solve the problem by sheer force of will where no tool can help you.
Is this just your kind of academic brain seeking out perfection and not finding it?
That and my grad student brain trying to do things repeatedly and failing and saying that, well, maybe this doesn't work. And yeah, so my unpopular opinion is that software engineers basically have job security and computers won't replace them.
Oh, there you go. I think that's going to be very popular. We will test this on Twitter.
But not in my academic niche.
No, it's not good for you at all. At all. No. Are you going to quit and do something different or sticking with it?
No, I think I wanted to, push it as far as it will go, but keep in mind that maybe it won't be infinitely far.
That's amazing.
I think we'll all slowly get to be more like prompt engineers, which is sort of maybe the next level of abstraction, but not necessarily, but we'll basically be guiding the AI to do things for us, among them programming. And it's technically natural language, but it's not exactly the English we're using every day. And we all come with different Englishes. And while we understand each other, the computer understands it a bit differently. So it will be basically sort of a next level of programming. So in some way we will automate ourselves out of job, in other way we'll just have new jobs.
We could just write the tests. I feel like even with the fuzzing thing, it could make this work.
So you say that, but that is a thing. Like I have friends who are researching that. It's called synthesis. And it's basically you write the specification of a program and like the tests are specifying what the program should do. And synthesis, like either again you do machine learning or you just search every program possible in like a very specific and way that makes it actually find programs sometimes, and you can make programs that way. You can do programming. So Excel, if you think about it, and all the autofill things that it can do is basically this: you write what you want it to output, and then you drag it, and then it figures everything out. Especially with the new features they added.
Oh, yeah, I haven't seen them. I tried it the other day and I'd put 1, 2, 3 and then it just repeated 1, 2, 3 loads of times. I was furious. I was absolutely livid. But actually, right, if it's doing that with the code, I mean, if it's got things like that points to analysis where it understands the memory use and performance and things, it could even then optimize code. Like it could like give you an early version and over time just keep sort of improving it and things. And that does get very exciting when you think of that running at scale.
So again, my unpopular opinion is that will never happen, that the best it can do it, it sort of points you in the general direction of saying, well, maybe you want to look at this could be a good place to look at, but it will never be able to do that by itself. It will never know enough about the programmer to do it.
Interesting.
Yeah, because even like programs we write, they contain bugs. I had a manager once that said, he doesn't want any more bugs in the code, right?
So just don't write any more code, no more bugs. Easy.
Yeah, there you go.
No code. No code is the future.
There's definitely truth in that, but genuinely though, like, yes, it's about whether the program does what we want it to do.
Yeah.
Like based on a criteria that's external to that program, isn't it? So in a way, it's not available to it to know that. But yeah, I don't know. Could you write a test?
But even the tests don't specify the program completely, right? We all know that writing tests is hard, right?
Writing good tests is hard, isn't it?
Writing tests that are a good specification is even harder because, well, if you tell it to, multiply, you get 2, you get 2, it goes to 4, then okay, yeah, I can write a program that always outputs 4. That works, right?
That's why you need more than one test case.
Exactly.
Yeah.
It will almost be adversarial in that it will always find the way that, it can do the thing that you don't want it to do instead of the thing you wanted it to do.
Yeah, also what you want can change too over time. It's quite interesting. Using static analysis, could you check to see that tests don't contradict themselves?
Oh, that's an interesting question. I suppose you could, but it depends what you mean by contradict themselves. You could use static analysis to extract them somehow and compare them and see. You definitely could do that. You could see if what they say about the method that they're testing, if they're unit tests, so you really test a method, if that's consistent, if it can think of a method that outputs a certain thing. So if a static analysis, let's say you have a method that returns some integer, then we have various sorts of integer analysis that can give bounds. This output is between 0 and 8. Give it an interval. That's interval analysis. There are more complex types of integer analysis that try to figure out what the value can be, and it can definitely figure out that there's a contradiction somewhere.
Yeah, that is interesting. I guess that's why pure functions like Rust has, that must be a much easier problem set, like a much easier language to work with than Go, because you can have side effects to methods and functions in Go.
So static analysis, it doesn't really care about the side effects because it's not executing anything.
Yeah.
If you're reading input or something like that, then obviously you have no idea what value it is or what value might be. But you just mark it as top and keep going. And it can be anything. That's fine. I'll just put that into the analysis.
That sounds really cool.
All right, folks. That was very interesting, and that developed even in a more interesting direction after the unpopular opinion. I already wonder what is the next episode we're going to do about this. Until then, thanks everyone who joined us. Have a great rest of your day.
It's time now for a quick shout at, where we pick an upcoming community event and shout at it. Go West is a Go conference for the Mountain West region of the U.S., and this year's event will be held in Utah and remote on October 21st. The organizers are still accepting talk proposals, but the CFP closes May 22nd, which is less than a month away, so you better get on it. Learn more at gowestconf.com, and we'll put a link to the CFP in your show notes. If you dig Go Time and you're not also subscribed to the changelog, you're missing out on some seriously good stuff. We had Brian Kernahan on the show, and I asked him what Unix and the web have in common and if it can help explain their success. Here's what he had to say.
Fundamentally, it's the core simplicity of the thing. These are not complicated. They are simple. The essence of Unix is a handful of ideas that work really well together. I mean, the hierarchical file system, the programmable shell, redirection, not too many system calls, and interestingly, text is kind of the universal medium of exchange of information. Now you look at the web. What are there? There's, if you want to call them system callsy kinds of things, there's HTTP, HTML, the URL. That's it. There is nothing else. Yes. It's got the internet as an infrastructure. Oh, and everything that goes across the web is text. So that commonality, I think, is quite real.
Listen and subscribe to the changelog at changelog.fm. As always, this episode has Fastly on CDN, Breakmaster Cylinder on the Beat Machine, and you making it all worthwhile. We appreciate you listening. Next time on Go Time, Johnny is talking PHP and Go. Stay tuned for that. We'll have it ready for you next week.